Hello, everyone. I'm Ekaterina Savchenkova, and today we are going to consider exponential functions and their derivatives. So we are going to start with definition. What is an exponential function? The function which looks like this: f of x equals a to the power of x, where a is a positive constant. It's called exponential function. Positive constant means that it's greater than 0, can be any number, but it's not going to change while we are changing x. The only argument here is x. Exponential functions are going to have three basic graphs and basic shapes of the graph. And depending on what is a, if a is greater than 0 but less than 1, how the graph of exponential function is going to. Let's just kind of check how it's going to look using just some actual example. My whiteboard is not reacting good way. By the way, guys, we are going to do some graphs in this class, right? So please look how I draw and label my coordinate axes. So coordinate axes are going to have arrows only at two positions: positive direction of x-axis, positive direction of y-axis. Also, axes must be labeled with variables or like dependent or independent variables which we are using. For example, here I'm using x and y. Also, supposed to have 0 showing where is origin. And usually, guys, I would suggest you to label one unit on each axis. It's not necessary to label like 1, 2, 3 until like 20 or 100, but one unit on each axis just to show what is your scale. I'm going to consider, for my example, a equals 2. So I'm going to graph function y equals 2 to the power of x. To do that, I'm going to build a table. So how my table is going to look? Well, this is a good idea to remember how I build a table. So next time when you do it, you probably either going to remember the shape of a function or just kind of recall the table is going to look like that. Yeah, normally, guys, of course, if you are not a human being, but a big computer, you probably are going to just use multiple points, substitute them instead of x, and calculate what is going to be 2 to the power of that multiple points, and kind of just have a big table which you graph. But I'm not a big computer, so I'm going to calculate actually very few points, which are going to produce like a approximate shape of the graph. So I'm going to label my top as x, my bottom as y, and I'm going to consider next points. My first point is -1, sorry. My second point is going to be 0. My third point is going to be 1. And my fourth point is going to be 2. Generally speaking, when I graph exponential functions, I even don't use 4 points. I usually use 3 points. But for this first time, we are going to use 4. So what is going to happen when we have 2 to the power of -1? Let's kind of write it down. 2 to the power of -1. You remember that it's actually 1 over 2 to the power of 1, right? The -1 means that actually that's a denominator of like the power sits in the denominator. So what is this? This is 1/2, right? Well, I'm just going to write down 1/2 over here. So let's kind of recall what is 2 to the power of 0. By definition, all numbers to the power of 0 are making 1. So they are going to have 1. This is going to be a same point for all exponential functions. So every time when you raise any number to the power of 0, you are going to get 1. Okay, the power of 1, well, kind of easy to imagine. So 2 to the power of 1 is going to be just 2, and that's also a very nice point to remember, right? So any number to the first power is just a number itself. And 2 to the power of 2, kind of easy. 2 to the power of 2, it's 2 by 2, which is going to be 4. And I'm going to write down here 4. So now what we can see that we have 4 points. 1/2, 1, 1, 2, 2, 4, and they are going to start as -1 as x and go up to like 2 as x. I'm going to stretch a little bit my graph to just kind of make it easier for me to graph. So minus x minus 1, y equals 1/2. So we have -1 here, 1/2 is somewhere here, right? And the next point is 0, 1. So 0, 1, well, it's already on the axis, so it's already having a mark. So my point is going to be kind of bigger, a little bit bigger. So when x equals 1, we are going to have 2. X equals 1, we are going to have 2. And when x equals 2, we are going to have 4. When x equals 2, I'm going to label actually 2 over here, and we are going to have 4. Y equals 4, 1, 2, 3, 4. So that's my point. So I have in total 4 points. I'm going to connect them with a smooth line, curve, I would say, actually. And kind of continue the curve a little bit to the right and a little bit to the left. That's how the graph of typical exponential function is going to look. The only thing I'm sorry, guys. I wrote that I'm going to consider the graph from 0 to 1, but actually I used 2 as my not very good, but we can easily fix this by changing a little bit our inequality. I think I was too absorbed fighting with my Zoom updates and my whiteboard updates. So actually, well, 2 is not less than 1, right? 2 is actually greater than 1. So right now we are working with a case and A is greater than 1, but that's our kind of typical case. So usually how it's going to look. So the curve is going to look this way. And what we can say about this curve? Well, let's imagine that we start continuing this curve toward positive axis. Like increasing my x is going to bring us bigger and bigger powers of 2. Bigger and bigger powers of 2 are going to bring me eventually to a very huge number, right? 2 to the power of 2 is 4, and 2 to the power of 3 is 8, and 2 to the power of 10, it's 1064, I think. So what does it mean? It means that when I'm increasing my x, my function grows, and actually the limit, I'm going to write it down over here, the limit of 2 to the power of x as x goes to infinity is going to be also equal to infinity, right? Because the result is increasing while you are increasing x. What is going to happen if we go to large negative axis like -1 we have over here, right? That's -1, -2, -3, -4. Well, we are actually going to increase the number in denominator. Same way we were increasing like the number, just put this huge number in denominator. Of course, what is going to happen when you divide 1 over a huge number in denominator? We are going to have something very small. And very small means that limit on this side will go to 0, limit of 2 to the power of x as x approaches negative infinity is going to be equal to 0. So it's very good to know what are the limits of exponential function, kind of remember them. So that was my first function, and we considered limits and just build it. Now let's build 2 other exponential functions. And somehow I kind of maybe forgot how to use my whiteboard. I don't see where I can change the color of my, over here, the color of my pen. So let's consider the next case, and let's consider the case which I kind of wrote in the beginning, but kind of started doing opposite. So let's consider the case when A is actually between 0 and 1. So, well, what kind of number we can consider as A? Let's consider A equals 1/2. Why I'm doing 1/2? Well, I'm planning to build a symmetrical to the graph of A to the equals 2 graph. So we're going to have a function y equals 1 over 2 to the power of x. As we probably remember, when we raise a fraction to a power, we can raise 1 to the power of x, and here 2 to the power of x. Well, 1 to the power of x is still going to be 1, and we are going to have 1 over 2 to the power of x. Well, what we can do, actually, we can do a similar table, which we had over here, right? Similar to this one, and just kind of graph using the points. Now, guys, I'm going to be on my laziest side, and I'm going to just do 3 points. I'm going to label x, and that's going to be -1, 0. Sorry, somehow I pressed something and my whiteboard disappeared from my screen, not from yours. 0 and 1 over here. So let's calculate what we are going to have as y. So when x equals -1, we have y equals 1 over 2 to the -1. We are going to second place. So we remember that actually when we have the power equals to -1 means that it's a denominator. So basically we're supposed to have 1 to the power of divided over 1/2. Division by a fraction, it's actually multiplication by inverse fraction. And inverse of 1 over 2 is 2 over 1, right? And we are just going to get 2 over here, which I'm going to put over here. 0 is still going to have the same rule. When x equals 0, y is going to be 1 over 2 to the power of 0. And we remember from the first time, from the previous function, that it's just 1, and we have 1 over 1, which is going to be 1. And the power of 1, very convenient one. When x equals 1, we are going to have 1 over 2 to the power of 1, which is going to just give us 1/2. So I'm going to put 1/2 over here. Now let's graph what we are going to have as a result. I'm sorry, guys, I kind of lost my skills for a couple of last years. I was teaching classes on the board again, and I kind of lost my skills of using the notebook or like recording equipment. So guys, again, we have x-axis labeled as x-axis with arrow. This arrow symbolizes or shows positive direction of x-axis. Y-axis labeled as y with arrow showing positive direction of y-axis. 0 labeling origin point, 0, 0. And 1 unit on y-axis, 1 unit on x-axis. Let's graph these 3 points. Yeah, I wanna use a different color for graphing what we have. Let's use pink. So my first point is minus x equals -1 and y equals 2. So when x equals -1, y is going to be equal to 2. 2 is going to be somewhere here. So the point is going to be here. Next point, 0, 1, right? When x equals 0, the point is 1. And when x equals 1, the point is 1/2. Well, now I'm just going to connect these 3 points with a smooth curve and kind of extend it a little bit to the left, a little bit to the right. Well, that's my second graph. If you look or compare my first graph and second graph, besides that they are a little bit different by size, they are looking like a reflection of each other or y-axis, and that's actually going to be true. So if your A's are reciprocal fractions or reciprocal numbers, they are going to produce graphs which are reflections about the y-axis. Let's label the limits of this graph. Now we can see easily that when x goes to infinity, the number is going to become smaller, smaller, and smaller. Like when x goes to bigger numbers, we're going to have, like, let's look over here. We're going to have bigger and bigger x, producing a bigger denominator, which is going to produce a very small number when you divide by it, right? So the limit over here is not going to be limit over here when x approaches infinity of 1/2 to the power of x will be equal to 0. And on this side, we see that when we raise two negative powers, we are actually going to have these two numerator in two positive powers, which is going to produce a larger number. So the limit over here, this side is going to be 1/2 to the power of x is going to be equal to infinity. You see that limits are kind of opposite for these two cases of A, right? Kind of complementary to each other, and the graphs are complementary. The only case we did not consider was the case of A equals 1. Why I did not consider it? Well, just because I thought maybe you guys can do it by yourself, but actually thinking maybe I should consider it. So let me just consider this last case. When A equals 1, my function y is going to look like 1 to the power of x. We do know that 1 to any power is going to be equal to 1. So actually, my function in this case is going to be just a constant function, y equals 1. And that's why I was keeping this case to the very end. So that's going to look like this. Y over here, x over here, 0 here, 1 unit here, and 1 unit here. So that's how it's going to look. So we have kind of three cases. Maybe I should unify them into one graph so you guys are going to understand a little bit better how they look like next to each other. So case like this, we use. Well, I'll try to make it like reflection as much as possible. So guys, for blue one, A less than 1, like 1/2, but greater than 0. For pink one, A is greater than 1. And the black one is A equals to 1. So these are graphs of the exponential function. Okay. So we did the graphs and we did the limit. Now, guys, how do we differentiate exponential function? Let me move to our next question. Maybe I use it. Perfect. We scroll it up and derivatives of exponential functions. Derivatives of exponential functions. Well, guys, let me remind you what is a derivative from our calculus 1 or 5a. Derivative of function f of x at point x, f prime of x, is a limit as h approaches 0 of f of x plus h minus f of x divided over h, where h is a small increment or difference from point x where you are searching for a derivative. And we remember that what is this actually? Derivative is a limit of secant lines between, like this is a slope of secant line which goes through the point x and x plus h of the function. And if we do the limit of this h, or make this step from the point x infinitely small, we are going to have, instead of secant line, we are going to have a tangent line, and derivative, it's actually slope of tangent line, right? What we are going to have in our case, if I apply this formula to our function f of x equals a to the power of x. Well, let's just kind of write it out. A to the power of x derivative equals limit a to the power of x plus h minus a to the power of x divided over h, and h goes to 0. I'm going to simplify this expression a little bit. And what I'm going to do for the first term, I'm going to represent it as a product, as a to the power of x by a to the power of h. Okay, why I'm doing this? Because I'm planning to take something outside of parentheses. You still remember the rule that if you do have two exponents with the same base, you can add the powers, right? But instead of adding the powers, I'm going to subtract them. A to the power of x here divided over h, and h goes to 0. Next step, because I have a to the power of x in both terms over here, I'm going to take it outside of parentheses. And I'm going to have a to the power of x, and in parentheses, I'm going to have a to the power of h minus 1. If I take a to the power of x from this term, I'm just going to have 1 left, right? And divide it over h. H goes to 0. Because my a to the power of x does not depend on h and doesn't have h anywhere, we can take it outside of the limit. We can take it outside of the limit. And that's what I'm going to do. I'm going to put it in front of the limit, and under the limit, I'm going to have a to the power of h minus 1 over h. Sorry, just a second. So h goes to 0. Now, guys, I'm going to do one little thing, which unfortunately kind of going to be a voluntary thing, I guess. But I'm going to set up a definition. There is one point in like introducing exponential function definition or derivative to set this definition. So let's define function. Let's define number e as a number for which this limit is going to be equal exactly to 1. Wow, it looks a little bit strange. So we are defining a strange number e, and like telling, okay, for the strange number e, the limit must be equal to 1. And the question is how it's going to help to us. Well, first, what we can do, guys, remember that we always can do numerical calculation of a limit. You just take different days and plug it over here and start take different ages and look like how the limit behaves. And eventually we are going to realize that for a certain number a's, the limit will go to a number. Well, it's going to be a different number for each a. And eventually, one of these numbers for which limit goes will be 1. And if you take that number which you used for a, which is producing 1 as a limit, and label it as number e, then our derivative of such number is going to look next way. E to the power of x. Now, instead of a, I'm using e because I have a special knowledge about this limit for that number. I'm going to have, instead of a to the power of x, I'm going to put e to the power of x. And here I'm going to just copy the limit e to the power of h minus 1 over h goes to 0. And because I kind of search for such number which is turning this limit into 1, then my derivative is going to be just e to the power of x. There are many different definitions of number e. Well, you probably recognize that we label with number e the base of natural logarithms, right? There are many different definitions of number e. So in this class, we're just going to introduce this definition. But it does not mean that like all other definitions are not going to work. It depends on how you build like a theory in the class. And for our class, it's going to be convenient to introduce number e, not other way, but this strange way. In some classes, or in some courses, number e is introduced as the base, which is producing a function which has a derivative exactly equal to itself. So you differentiate the function and get the function, same function back. So in some courses, e is introduced this way. Okay, but we are going to introduce e as a special number which is turning this limit into 1. Well, so far, guys, we learned how to differentiate to the power of x. It's a strange number, which is going to be called the base of natural logarithms. And that's good. We don't know how to differentiate all other numbers. Like, for example, we still don't know how to differentiate 2 to the power of x. We don't know. Or 1 over 2 to the power of x. We still don't know. Only one function we know how to differentiate is e to the power of x, and the derivative of it is e to the power of x. We are going to learn these two in the next class, or like say next lecture. For now, we're going to concentrate on exponential function and learn some funny stuff about it, like how to use it, how to differentiate. Well, of course, because the derivative of the function is so simple, no one is differentiating the function just by itself, but usually people are differentiating the compositions of this function or a mix of this function with some other functions. Let me consider a couple of examples. My example number 1, I'm going to consider function y equals x squared by e to the power of x, and I'm going to differentiate it. What is going to be the derivative? Well, because it's a product of two functions, I'm going to use a product rule. Product rule means that I'm going to differentiate my first function first, which is going to be 2x, right? Multiplied by my second function. Then put plus, copy my first function, and differentiate my second function. Derivative of e to the power of x is still e to the power of x. I'm going to get e to the power of x here. That's going to be my derivative. We can simplify it a little bit by writing down e to the power of x up front and copying 2x plus x squared over here. You even can simplify it more by placing x. I think that's going to be enough. And this my second example is going to be differentiate a composition. Imagine that my function now it's e to the power of x squared. How do I differentiate this one? I remember that to differentiate composition, I'll need to differentiate first my outer function, considering my argument as just u. So derivative of e to the power of u is e to the power of u, right? So I'm just going to copy e to the power of x squared. Then I'll need to differentiate my argument, multiply by derivative of the argument. Derivative of x squared is 2x, and that's going to be my final derivative. Okay? That's all about differentiation. Now, guys, let's see how the graph of the function is going to look, and then discuss a little bit how to integrate the exponential function. So now let's consider function f of x equals e to the power of x. Well, let's pretend that I did not tell you, but e actually has a number 2.71828, and some lots of digits after. The number is going to continue infinitely. It's never going to have a period. E is a very special number. It's not only irrational number, which is not going to give you any periodic repeating pattern, digits after the decimal point. It's also a transcendental number, so it's not a solution of any algebraic equation. Okay, one of two special numbers in our world. The second number is pi, right? And they both are about like equal to 3. Okay, so, well, because this 2.7 approximately, it's obviously greater than 1, the graph of exponential function is going to look the way of 2 to the power of x, right? It's going to look like this. This is going to be 0.1, this is going to be y, this is x. Well, at 1, it's going to be equal about like 2.7 and something like this. What are going to be the limits? Limit over here, e to the power of x as x approaches infinity is infinity, right? And on the left side, as x approaches negative infinity, is going to be equal to 0. Okay. Okay, that was just a few words about exponential function. Now, guys, maybe we can calculate an interesting limit for exponential function before we talk about integrals of exponential functions. So let me consider an example of possible limits of exponential functions. I'm going to label example 3, and my example is going to find the limit e to the power of 1 over 2 minus x as x approaches 2 plus. You probably guys are going to look at this weird limit and tell me like how it's connected to all the stuff we learned besides it has e. Well, let's start with 2 plus. 2 plus means that we are going to approach 2 not from any direction, but specifically from positive direction. The plus means that we go from the right to 2. So we can use all numbers greater than 2 in our limit, right? Now, we don't know what is a limit of e to some kind of composition power, but we do know that limit of e to some big positive number is infinity and the big negative number is negative infinity. What I'm going to do, guys, to make our life a little bit easier, I'm going to use a substitution. I'm going to label u equals 1 over 2 minus x. Now, let's find out what is going to happen with u. What is the limit of u when x goes to 2 plus? Well, that's going to be limit of 1 over 2 minus x as x goes to 2 plus. Well, when we are approaching 2 from the right, our numbers are a little bit greater than 2, like 2.1, for example. If I plug over here 2.1, I'm going to get 2 minus 2.1, which is going to give me a small negative number. So I'm dividing 1 by small negative number. And if this negative number is becoming even smaller, we get closer to 2 on this. We are going to have 1 divided by a very tiny negative number, which is going to produce negative infinity, right? Because when we divide a constant by some small number, we are going to get infinity. But when this number is negative, we are going to get negative infinity. So we know that u actually, when x approaches 2 plus, is going to approach negative infinity. So what I'm going to do is I'm going to rewrite my limit in terms of u. Limit e to the power of u. And this u, when x approaches 2 plus, u will approach negative infinity. Now, we can compare our limit to what we know about exponential function. And we see that this limit is similar to the left limit of exponential function. When argument goes to negative infinity, limit goes to 0. So we calculate the limit. That was the answer. Okay. Now, guys, let's talk a little bit about integration. And I think that's going to be all for today's lecture. Integration. Of e to the power of x. Yeah, guys, we're not going to integrate actually any base to the power of x. We are specifically going to integrate e to the power of x because we still don't know what are derivatives of any other base besides e. So we're going to use the fact that derivative of e to the power of x is equal e to the power of x. That means that integral, sorry guys, I pressed something on my computer. E to the power of x dx. Which function we differentiated to get this e to the power of x? Well, we differentiated that e to the power of x. The only difference between just this answer and like what we're supposed to have for indefinite integral is going to be a constant. because when we differentiate this expression, we're not going to get e to the power of x with plus something, but derivative of a constant is 0. So that's my indefinite integral. Let's integrate something. For example, that's going to be my example 4. Let's integrate x e to the power of x squared dx. Let's find the indefinite integral x e to the power. Well, guys, when you see something like, which we don't know what is integral of e to the power of x squared. We actually do know only e to the power of x. It's supposed to tell you that you're supposed to use a substitution here. In our case, substitution is going to be u equals e to x squared. So what is going to be du in this case? Well, if I differentiate this, derivative of x squared is 2x dx, right? If I look at my expression over here, I'm going to see that I do have x dx over here already, right? The only thing I don't have is 2. So what I can do, I can write down that du divided over 2, I'm going to move this 2, this 3, is equal x dx. And now I'm going to write down e to the power of u, because x squared is my u. And instead of x dx, I'm going to write down du over 2. Now we remember that any constant can be taken outside of the integral, and you have e to the power of u du, which is going to be just a standard integral. 1/2 e to the power of u plus a constant. But because u is not our original variable, we are going to go back to x squared and have 1 over 2 e to the power of x squared plus a constant, which is going to create our final answer. Well, that's how we integrate exponential function. Now, guys, well, it's not like much more theoretically to explain, and I don't want to make this lecture very, very long. So what I'm going to do, guys, I'm going to write down some questions below, which I want you to consider like as a homework or as preparation for actually our Wednesday meeting or doing self-work. Going to be too many of them, like just few questions. Okay. Let's kind of start with finding the limit. Question 1, find the limit. Limit 2 to the power of negative x minus 1 as x approaches infinity. And there is going to be one more question about finding the limit. And that's going to be limit of e to the power of 3 minus 2 minus x as x approaches 2 minus. So 2 limit questions. Question 2. Well, I'm going to put some derivatives, differentiate. Right? Maybe you can see. So I'm going to write down the function, and for all functions, I want you to find the derivative. My first function is a square root of x, e to the power of x. My second function is e to the power of cosine of x. Third function is e to the power of 1 over x. And fourth function, star, super complicated one, is e to the power of e to the power of x. Or a little complicated function. For integrals, I'm just going to give you like 3 integrals. Find the integral. And the first one is going to be e to the power of square root of x divided over square root of x dx. Second one is e to the power of x 1 plus e to the power of x. In all cases, you will need to do substitution. And the last one is going to be indefinite. It's going to be definite integral, sorry. Integral from 0 to 1 e to the power of negative 3x dx. Well, let me see how many questions I placed. Okay. So guys, many questions we have. We have like 7, 8, 9, 9 questions over here. 2 limits, 4 derivatives. If you don't know how to do some of them, kind of you can skip them. But my idea is that you try all of them. And 3 integrals. Okay. And we are going to consider these problems during our Wednesday meeting, but makes sense to kind of try them on your own, like considering what you learned from this lecture. I think that's all for today, and I'm going to say goodbye and see you Wednesday.